Hello and welcome to this video on how to run a multi-group confirmatory factor analysis in the free JASP software. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, path analysis, multi-level analysis, latent class modeling, and other techniques. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including workshops that I offer through QuantFish. In this video, I want to show you how you can run a multi-group confirmatory factor analysis for free and with a point-and-click software that is very user-friendly, namely the JASP software that you can download for free from the internet. I included the link to the software in the description for this video, so check it out if you haven't already. It's a very nice, very user-friendly free program, point and click, that does a lot of things, not just basic statistical analyses, but also more advanced techniques such as factor analysis and structural equation modeling. And I have a whole playlist on this channel on analyses with JASP. I'd also talk about how to do conventional factor analysis, both exploratory and confirmatory, how to do path analysis, mediation analysis, structural equation modeling, reliability analysis. So check out that playlist or the videos on those topics if you haven't already seen them. So now let's go and get ready. Let's get ready to run a multi-group confirmatory factor analysis. First of all, of course, you need data. And one nice feature of JASP is that it allows you to directly open an SPSS data file if you have your data in SPSS format, or you can open a simple text file, .txt. You can very easily edit your data under this option edit data that you can see here. So you can change the variable names, the scale level, and you can have a description and a variable label. So it's very, very nice the way that JASP allows you to do that data editing as well. You can see in my example data file that I have open here, which was a text file originally, and now I saved it under the JASP file format. In this data file I have a grouping variable, so this is a nominal variable that has two groups, and I have four variables, y1, y2, y3, and y4, that are metrical or scale level variables. As you can see here, that's defined, that shows this little metric scale symbol. And so now what I'm going to do is I'm going to run a two-factor confirmatory factor analysis model where I have one factor for y1 and y2 and another factor for y3 and y4. And I'm going to use the group variable here as my multi-group analysis defining grouping variable. So how do we do that in JASP? We go to factor and then confirmatory factor analysis. And that's what you would also use for a single group analysis. So that option you would use if you had a regular CFA with a single group. And I have a separate video on how to do that. So if you're interested in single group CFA, then check out that video. So now we have a multi-group analysis. And first of all, the multi-group analysis works in the same way as a single group analysis in JASP. You first of all define your factors. And you can see that in JASP on the left-hand side, we have our input window that looks similar to a dialog window that you would have in SPSS, except that SPSS does not allow you to do this multi-group confirmatory factor analysis, but it works in a similar way as SPSS, and it's actually really intuitive. So we have a factor 1 here already, so we're going to move y1 and y2 over to that factor 1. And then on the right hand side in our output or results window, it says the model could not be estimated. And that's because a single factor with two indicators is not identified unless you put in additional constraints. So this doesn't work, but don't worry, we're going to add a second factor. So by clicking on this plus symbol here, I'm going to show this again. So here you have a little plus symbol. You can add another factor. So it's very convenient. And now we're going to add y3 and y4. And we're going to put those on factor 2. And oh, you can see now the model is identified with 1 degree of freedom and it can be estimated. And you already get your chi-square test of model fit for a single group factor model with 2 correlated factors on the right hand side. Now this model, why is it identified even though each factor has only 2 indicators? It's because the factors are correlated. And so when you have a substantial correlation between the factors, as you can see here under factor covariances, you can see that factor covariance of 0.344 is statistically significant. So the factors are substantially correlated, and then the model is identified even when each factor has only 2 indicators. I have a separate video on that topic in case you are more interested in identification with 2 indicator models. I discussed that issue in more detail in a separate video here on this channel. Now, another thing that I want to show you before we get to the multi-group specification is that you can actually also include a factor label. So rather than calling this factor 1, you can call it whatever you want. So you could, I don't know, you could call it construct 1 or whatever label is more appropriate. So that way, or that you like better, so that way it's also nice because then that shows up in your output. And you can see that the output here is interactive. So when you change something in the input window on the left hand side, the results section changes. So rather than producing more and more and more and more output like SPSS, for example, where you have to rerun everything if you want to change something, the results window will not completely explode and will not give you unlimited amounts of output if you change something. So that's also kind of nice. So this stays manageable. And so next, where do we find our multi-group option? You can see it's a separate option here on the left-hand side called Multigroup CFA. So we're gonna click on that. And then you can see that right now no grouping variable is chosen. Therefore, it's a single group analysis. So that's a regular single group 2-factor confirmatory factor analysis model with correlated factors. And so now when we choose a grouping variable here in this little drop-down menu, then this will be turned into a multi-group analysis. So it's really clever. It's a really intuitive, user-friendly way that JASP does this. So click on that. And then automatically what you get is by default a configural invariance model. So what does this mean, configural invariance? You can see that here under on the right hand side next to the grouping variable. You can see that this is now set to configural. Configural is the least restrictive multi-group model where across groups you have no invariance constraints other than that those that are needed for identification of the model, but you have freely estimated factor loadings, you have freely estimated intercepts, and you have freely estimated error variances. And so this only assumes that you have the same factor structure, the same number of factors across groups, the same loading pattern, but not any constraints, any equality constraints on loadings, intercepts, or residual variances. And so you can see here that we get the factor loadings, or first of all, we should check the model fit, which here what is given by default is only the chi-square test. And you can see that the model fits the data very well. So our factor model is the second model here. It has a chi-square of 0.229, 2 degrees of freedom, and a p-value of 0.892, so it's not rejected. The baseline model is the null model, which we don't need to consider here. It's always a poorly fitting model. And so our model fits the data well because the p-value here is not significant, which means the model is not rejected. It does not deviate significantly from our observed mean and covariance structure. Next, as I already mentioned, we have the factor loadings, and right now we have the same loadings in group 1, sorry, not the same loadings in group 1, excuse me, as compared to group 2, because this is the configural model. So the configural model does not constrain any of these loadings to be equal for a given indicator across groups. So you can see they're all different. And so that's what we would expect under configural invariance, that the loadings can be different, that they're not constrained to be equal. The factor variances here by default in the configural model are all fixed to 1 in JASP. So that's the way that JASP identifies the model. So we have, so say, equal factor variances, but it doesn't mean anything because the loadings are different. We also have freely estimated factor covariances. You can see they can differ across groups. Here they happen to be quite similar, but also this doesn't mean a lot right now because we don't have our final model yet. The residual variances also are allowed to differ. Now notice that in the default specification in JASP, no mean structure is included, meaning there are no intercepts or factor means. And so in order to get those, we have to go to model options and we have to check this little button that says include mean structure. And that's important because in a multi-group analysis, we also consider the factor means and the intercepts, because when we test later our scalar invariance model, meaning the model with equal loadings and equal intercepts, then we have to include our mean structure, and we're interested in mean differences at the factor level also, and so therefore the mean structure should be included. Now in the configural model it's less important because in the configural model there's no constraint on the mean structure, and therefore whether we include it or not doesn't really change anything. So you can see that when we include the mean structure here, our chi-square does not change, so that doesn't do anything to the degrees of freedom or the model fit, but we now get the factor intercepts here, which really are factor means, and we get the intercepts of the indicators. And so those just simply reflect the observed means now, and they're not constrained to be equal across groups because, again, this is the configural model, okay? So here you have your configural model, and one important finding, or maybe the most important finding, is that this model is not rejected. And so that's important for us because only when the configural model is not rejected are we allowed, so to say, to move on to more restricted models like a model with equal loadings. If the configural model were rejected, then we wouldn't do that because then the other models could only fit worse. So that's great that this model fits the data well, which means it makes sense for us to move on to more highly constrained multi-group models with constraints on loadings, intercepts, etc. So let's go down, and you can see that we have additional options in our drop-down menu here under multi-group CFA invariance testing. We can move on to the next model, which is the metric model. Metric means equal loadings. So now the loadings will be constrained to be equal across groups. This is also known as weak measurement invariance or weak measurement equivalence. And so this model now, first of all, we should check its fit. You can see that the chi-square is 1.46 for this model. 4 degrees of freedom. We gain 2 degrees of freedom because now loadings are constrained to be equal. And the p-value is still very good, 0.834. So the model also does not have to be rejected. So that's good. You can see when you look at the parameter estimates factor loadings table that now for corresponding variables, the loadings are equal. For example, the first indicator has a loading of 1.554 in group 1. And the same indicator Y1 also has a loading of 1.554 in group 2. So the corresponding loadings for like indicators, for the same indicators, are constrained to be equal across groups. Notice that that applies to the unstandardized loading. So we're always talking about the unstandardized solution in multi-group analysis when we're doing invariance constraints. So the unstandardized loadings have to be equal. The standardized loadings don't have to be equal. And you can see that by clicking on advanced. So when you go to advanced, at the very end under standardization, you can click on standardization all, and then you get an additional column in your loadings table with the standardized loadings, and you'll notice that they're not equal across groups. That has to do with the fact that at this point we have not constrained the residual variances or factor variances to be equal across the groups, and therefore the standardized loadings are not forced to be equal even when the unstandardized loadings are equal. So keep that in mind. And next, so say the other, what we also notice is that now we have freely estimated variances in the second group under the weak invariance model in JASP. So in group 1, we still have both variances fixed to 1 for identification, but the variances are now freely estimated in the second group. We also have group covariances estimated and group correlations. So under standardized estimates all, we find the factor correlations, 0.39 and 0.34. You can see they're similar across groups. And we have the residual variances, which still are not constrained to be equal across groups. We have the factor intercepts, which are still all 0. So the factor means are still 0 under this model. And we have intercepts which are still not constrained to be equal, which is the reason why we cannot estimate factor means at this point, because the entire mean structure is eaten up or is consumed, so to say, by estimating the intercepts of all the indicators freely in both groups. Therefore, there are no degrees of freedom left in the mean structure to estimate those factor means in this model. However, in the next model, the scalar model, will be able to also estimate factor means, as we will see. So again, the conclusion here is that since this model, the metric model, fits the data well, we are allowed to move on to the next higher level of measurement invariance, and that is the scalar model. So you find this next here in the drop-down menu under invariance testing. Scalar means now we have equal loadings and equal intercepts. So now also the intercepts for corresponding indicators are constrained to be equal across groups. And we find that this scalar model or strong measurement invariance model also fits the data very well. You can see the chi-square is 3.806, 6 degrees of freedom. The p-value is 0.703, so still not statistically significant. So this model also does not have to be rejected. We see that the loadings are still the same for corresponding indicators across groups. You can check that here. Standardized loadings are not, as I explained previously, so those don't have to be equal, but the unstandardized loadings have to be equal across groups. And then the factor variances are constrained as before in the first group, and they're freely estimated in the second group. Also, we have freely estimated residual variances as before, but we do have constraints on intercepts now. And you see that in the last table, where you can see that corresponding variables across groups have now an equal intercept. Y1, for example, has an intercept of 3.469 in group 1 and also 3.469 in group 2, and so on. So all corresponding indicators have equal intercepts, and that defines scalar invariance together with the invariant loadings. Because of that, because now we have constraints also on the mean structure, meaning on the intercepts, we are now in a position where we can estimate latent means, at least in one group. And so that's what's done here by default, is that in group 1, the latent means are fixed at 0 for identification, but in the second group, the means are estimated. You can see that the first factor has a mean of 0.57, and that mean is statistically significant. And that has an important meaning for us, because it means that in group 2, the mean, the latent mean of the first factor is significantly larger than the mean for the same factor in group 1. So, and that may be of interest. When you do group comparisons, you're typically also interested in mean differences, in this case, latent mean differences. And so that's where you can find out about whether there's a significant difference. So the first factor has a significantly larger mean in group 2 as compared to group 1. The second factor has no significant or shows no significant mean difference. You can see that the p-value is 0.155, and so that's not significant. So meaning with regard to factor 2, there's no significant difference with regard to the means. So that's an important issue in the scalar model, or an important thing to look for is, are there significant mean differences? Those cannot be tested with configural or with metric invariance, because those don't have constraints on the intercepts. And so that's important for testing latent mean differences. You have to have at least scalar invariance or strong invariance in order to meaningfully test mean differences across groups. Next, we can also test strict invariance. Strict invariance means that loadings are invariant, intercepts are invariant, and also the error variances or residual variances. And we can, first of all, let's verify, let's take a look at the chi-square test. You can see the strict invariance model still has a good p-value of 0.203 for the chi-square test. So this is not significant, meaning even the strict invariance model is acceptable here, has an acceptable fit. And so now when we scroll down, we can see that now also residual variances for corresponding indicators are set equal. For example, 3.16 and 3.16 for indicator 1 across groups. So this is the same indicator and has the same residual variance now. You can still interpret the mean differences, and you can see the result is similar. Construct 1 has a significant mean difference across groups, construct 2 does not. So that can still be done with strict invariance, and we would in fact prefer the strict invariance model because it is more parsimonious, it has more degrees of freedom, it has fewer freely estimated parameters. One last model that you can test in JASP is the structural invariance model. So let's take a look at that as well. The structural invariance model has a not so good looking chi-square. So you can see when you impose structural invariance on the latent variable parameters, then the chi-square goes up to 53.479. It has 15 degrees of freedom and it has a very highly significant p-value. So that model is rejected. And so let's take a look at what structural invariance means. It means obviously all variances are equal. You can see they're now all fixed to 1, which implies they're all equal. So this model forces the variances to be equal. It also forces the covariances to be equal. You can see those are now constrained equal, and they're now equal to the correlations at the end because the variances are fixed to 1. So the factors are all standardized. So in that case, when the factors are standardized to a variance of 1, then the covariances are equal to the correlations. So that is a constraint equal. And also the means. You can see under factor intercepts, which really give you the means. Here the estimates, they're all fixed to 0, meaning they're assumed to be equal across groups. And that's not acceptable. So assuming equal latent variances, equal latent covariances, and equal latent means is not acceptable. So that model does not work. So we have to reject that. We have to go back to strict invariance. That was the best model that we could find here. Now, what else can you get in JASP? I already showed you can get the standardized solution by clicking on standardization all. Also, you can get a different estimator. So for example, you can do this also with categorical data, in which case you would choose the DWLS estimator, which is the same as WLSMV in Mplus, for example. That's an estimator for ordinal and binary data. You can use a different missing data handling method here, although with maximum likelihood estimation and continuous data, like in this case, I would prefer full information maximum likelihood, which includes missing cases in the analysis, and that's preferable when you use maximum likelihood. Also, another thing that you could use is robust standard errors or bootstrapped standard errors, which could be nice, for example, if you had non-normal data or other issues with your data. You could get a plot of the model if you wanted that. So you can generate a path diagram of your model in which you could even show the parameter estimates. You could even show the mean structure. So let's take a look at whether that could take a while for JASP to generate that picture. So this is one thing that will then appear eventually in the output. You can also get let's see if it's there. Not yet, it takes a while. Under additional output, you can ask for additional fit measures. So if you wanted to see other fit indices other than the chi-square test of model fit, then that can be added here as well. And you can ask for R-squared. So the reliabilities of the indicators, you can ask for composite reliability under this reliability option here, in which case you get McDonald's omega composite reliability as well as Cronbach's alpha. You could ask for modification indices. You could also take a look at the model implied covariances, the model residual covariance matrix for diagnosing problems with the model in case it doesn't fit. And What is also useful in JASP is that you can print the LAVAAN syntax. So JASP uses behind the scenes the LAVAAN package, which is an R package for estimating structural equation models, and LAVAAN really is syntax based. So when you have R or when you use R, you can directly use the LAVAAN package and it's all syntax based. And it's more flexible when you use the LAVAAN syntax in R as opposed to doing the point and click. You can specify more special models, and so then if you wanted to learn the syntax, you can find that in the output at the very end. You can find the model syntax, and that way you can learn how LAVAAN works. And you can see that now our path diagrams are generated here for our strict invariance model with the unstandardized parameter estimates shown here in those path diagrams or model plots. You can also see that we now have composite reliability here. Coefficient omega is given, coefficient alpha is given for each group and each factor, which is useful. And we have a table somewhere also with the R squared values now. Up above you can see R squared, so those would be the individual reliabilities of the 4 individual variables, whereas the table at the bottom gives you composite reliability, assuming that within a factor you would combine the indicators into a scale. So that's useful. That's a lot of stuff that you can do here. What is also very nice in JASP is that you have this little info button here at the top where it says show info for this analysis. And so when you click on that, you find a description of this analysis type with a reference to the LAVAAN software, which is used in the background. And you can see that when you scroll down, there's a description of multigroup CFA, where again you can take a look at what it means for a model to be configurable, metric, scalar, strict, structural. In case you don't remember, then you can look this up here. Also, there's a description of the additional output and so on. So that's kind of nice as well that JASP allows you to get this information here as well. I hope you found this video useful to learn more about how to run a multi-group confirmatory factor analysis in the JASP software. If you did, please consider subscribing to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.